Welcome everybody. So this week we're going to be looking at compactness in sentential logic. So remember, sentential logic is the logic we saw at the beginning of the course where the basic building blocks were seen as sentences, are propositions. So the basic building blocks were what then became atomic formulas in logic, in first order logic, which had actually more inner structure. In propositional logic, these basic blocks, they were just these variables a1, a2, a3, which could be either true or false, but they have like no inner structure. Okay, so we have no quantifiers, we have no elements, no terms, no relation, no functions, no constants, just sentential variables, which could be true or false, and ands, ors, nots, implications, and if and only if. That's all there was in the language, remember? So if not, watch those videos at the beginning of the class. Okay, so there is a version of compactness for this logic. It's essentially, it follows from the compactness for the other one. I guess you have to be set up the proof the right way. But we are gonna do it the other way. So we're gonna be able to prove compactness for this logic because it's simpler. For first order logic, we're gonna have to wait a few weeks. And still, even though if it's simple, we still get interesting corollaries for compactness for this logic, and we're gonna see this one of them. Okay, so now we have a set of sentential well-formed formulas, gamma, which is think of it as it being infinite, and we say that, remember that we said that gamma is satisfiable if there is a truth assignment that assigns to each sentential variable a1, a2, a3, all of them, either a true or a false, a Boolean value, a t or an f. All right, so each truth assignment is a function that assigns to each of these guys either a t or an f. And then, if you guys remember, once we have an assignment for all the variables, we can extend that assignments to all the formulas. No, so once the variables in the formulas can be true or false, we can tell if the whole formula is true or false. Okay, so we say that this whole set of formulas is satisfiable if there is one true assignment that makes all the formulas in that set true, okay, at the same time. So it's one truth assignment that works for all the formulas in gamma at the same time. And compactness is essentially the same statement as we had before. It says that if every finite subset of gamma is satisfiable, then gamma is satisfiable. And again, just doing the little exercise, you should always do this exercise when you see a theorem, why is it not obvious, or why it makes sense. So why is it not obvious? Well, the fact that every finite subset is satisfiable, that means that for every finite subset you can find some true assignment that is going to make those formulas true, but then maybe for some other finite subset you find some other truth assignments. And it's not necessarily obvious that you can put together these truth assignments. So this is saying that yes, that if every finite subset, if there is a truth assignment for every finite subset, then somewhat there is one that works for all of them at the same time. Okay, so similar to what we had before, and the same way, the same proof we used last week works here to prove this theorem, that if a set of sentences or well-formed formulas prove semantically implies. Now in the case of sentential logic, this is tautologically implies the formula phi, then there must be a finite subset of gamma that already implies the formula phi. Okay, so if every true assignment that makes gamma true makes phi true, then there has to be some finite subset of gamma such that every true assignment that makes that one true already makes phi true. Cool. Okay, so these two are easy to see, to be equivalent. So let's now prove it. So in this case, we can prove it without using completeness as we need in the other case. So what do we need to do? So we need to find a variable assignment that works for all of gamma. And we are going to do it one step at a time. Okay, so we're going to write the truth assignment first in A1, then in A2, then in A3, and do one variable at a time. We're going to decide what the value for them should be. Okay, and the idea is the following. We're going to define a sequence of compatible truth assignments, V1, V2, V3, which are defined only on the finite sets. So where Vn is only defined on the variables A1 all the way up to An, and no more. So not on all of them, just the ones up to A1 up to AN, and for each of them it's going to assign true or false. And when I say here that they are compatible, that these truth assignments are compatible, I mean that V2, the value, like V1 decides the value of A1, and then V2 has to respect that and extend it and return the same thing. And then these two tell you what the value should be in A1 and A2, and then this one adds A3, and then each one is adding one more value than before, but each one is an extension of the previous one. Okay, so they are all compatible. So then at the end we're going to have one variable assignment on all variables, right? So we need them to be all compatible. So how are we going to do it? So let's start with A1. So if every finite subset gamma 0 of gamma is satisfiable via some truth assignment that maps A1 to true, we let V1 of A1 to be true. So we are trying to define A1. The first step is to define A1. The domain of A1 is just A1, because from A1 to A1 is just A1. So all we need to say is what V1 is going to do on A1. And we're going to say the following. So we know that every finite subset of gamma is satisfiable by some truth assignment. That's the assumption. But now the question is it satisfiable by some truth assignment that maps A1 to true? So if all of the subsets are compatible with A1 being true, then we let V1 of A1 to be true. And then if not, we're going to let it be false. Let's write that down. Now, if every finite subset gamma 0 gamma is satisfiable via some truth assignment that maps A1 to false, we're going to let V1 of A1 be false. Okay? So in principle, we know that every finite subset is satisfiable by some truth assignment. Some of them might let A1 be true, some of them might let A1 be false. And in principle, it be that maybe some finite subsets require A1 to be true and some finite subsets require it to be false. So we're saying if that's not the case, if you can always compatible with A1 being true, let V1 of A1 be true. If you are always compatible with A1 being false, let V1 of A1 be false. Now, how do we know that one of these two has to be the case? Well, let's prove that. So one of these two has to be the case. Otherwise, there are finite subsets of gamma, let's call them gamma 0 and gamma 1, such that gamma 0 is not satisfiable mapping A1 to true, and gamma 1 is not satisfiable mapping A1 to false. All right, so the first one up here, we're saying that is because this is not the case. So if this is not the case, so if there is no gamma 0 that is satisfiable, that is compatible making A1 true, then it has to be one. It has to be some gamma 0 that is not compatible with it being true. And because of the second case, right here, if this is not the case, there must be some finite gamma 1 that is not satisfiable using a variable assignment that maps A1 to false. Okay? So where is the contradiction? But then gamma 0 union gamma 1 cannot be satisfiable neither mapping true 2 to true or 2 to false. Right, because there is no way. But we know it is satisfiable because our assumption is that every finite subset of gamma is satisfiable. So there is some true assignment that makes this true. And that true assignment either maps A1 to true or A1 to false. So that true assignment is going to contradict either this one or that one. So here's where we get the contradiction. Okay, so that's why one of these two has to be the case. Okay. The contradiction comes from assuming this otherwise here. Okay, so either every finite subset is compatible with A1 being true, or every finite subset is compatible with A1 being false, and then we choose whichever of these two. It could be with both. It could be compatible with both. We choose one of them, whichever of them is true. And then that's how we define V1. Okay, so that's only to define V1. So now we need to move on and define V2, and then V3, and then V4, and then we're going to define this. We're going to do this little by little. Okay, let's see how we define now Vn. So suppose we have already defined Vn, and let's define Vn plus 1. Vn goes from A1 all the way up to An to true false, such that every finite subset gamma 0 of gamma is satisfiable in a compatible way with Vn. So by that I mean there is truth assignment that extends Vn, that is compatible with the values that we have in Vn, that we have chosen in Vn, and that makes gamma 0 true. Okay, but each finite gamma 0 might be satisfiable by a different truth assignment, but always one that is compatible with Vn. That's what the assumption that we have. That's how we're assuming that we define Vn that way, and then now by induction we're going to define Vn plus 1, or recursion essentially. Okay, so now how are we going to do it? Well, it's very similar to what we did with V1, except that we have to be just a little bit more careful. So let's see what we did for V1 and change it a little bit. If every finite gamma 0 including gamma is satisfiable, compatible with Vn and An plus 1 being true, we let Vn plus 1 at An plus 1 be true. And of course, Vn plus 1, we know what the values are on the previous cases, because that's Vn. So we defined Vn already. So we defined the evaluation, this truth assignment on all the ways, on all the variables up to n, and now we're defining just one more, right? So we have all of these already. Now we need to define one more, and if it's always satisfiable, compatible with what we have so far, and one more, and An being true, then we let the new one be true. And the same thing if every finite subset, let's call it gamma 1 of gamma is satisfiable, compatible with Vn, and A1 being false, now we're going to let An plus 1 be false. Okay, and so why is the case that we always have one of these two cases? Well, because we know that every finite subset of gamma is satisfiable, compatible with Vn already, but then maybe on some of those assignments An plus 1 is being mapped to true, and in some of those An plus 1 is being mapped to false. So why is that we can always say that at least one of those two occurs always? Well, the proof is very similar to the previous case. So if this is not the case, if neither of them is the case, so if the first one is not the case, we know there is a finite subset, gamma 0 of gamma, that is not satisfiable with Vn and An plus 1 being true. So it's a finite subset, gamma 0, that is not satisfiable, compatible with Vn, An plus 1 equals true. And if the second one is not the case, then we know that there is some gamma 1 that is not satisfiable with Vn and An plus 1 being false. Gamma 1 is not satisfiable, compatible with An and An plus 1 being false. But then how are you going to get the contradiction? But gamma 0 union gamma 1 is satisfiable, compatible with Vn. So there is some truth assignment that is compatible with Vn that makes gamma 0 union gamma 1 true. And for that truth assignment, either An plus 1 is true or An plus 1 is 4. So for that truth assignment, we're going to have either that is compatible with this or compatible with that. So it cannot be the case that we got these two here, because that truth assignment is going to contradict one of those two. So here is that we get our contradiction, which came from assuming that this wasn't the case. So one of those two has to be the case. Okay, so either we can extend to let An plus 1 be true, or we can extend to let An plus 1 be false. So we keep on going like that, and we end up with a truth assignment defined on all variables. We went one by one with all variables, such that every finite subset of gamma is compatible with this particular truth assignment. But this truth assignment is telling you the truth of every little variable, right? So if you treat it, compatible with this just means that it makes it true. So that means that for all formulas in gamma, this truth assignment gives you true, because all formulas in gamma belong to some finite subset, let's just say itself, and it has to be compatible with this truth assignment, but this truth assignment is telling you about all variables. So compatible means that just makes it true, right? So there is no other way. So therefore, by this particular truth assignment V. Okay? So that's how we put these truth assignments together. By knowing that so each finite subset has a truth assignment that makes it true, we find a way to put them together. And the key is that one, is to decide at each step whether every subset is going to be satisfiable, making a n plus 1 being true, or every subset is going to be satisfiable, making a n plus 1 being false. Okay, so now that we have a proof of compactness for sentential logic, we're going to see some applications in the next video.